Hello YouTube, we're back. Alright, so if we go to Sage, dang it. Why isn't this coming up? That's not it. Was it this? There it is, math bar. I know, right? Alright, so let's make a new worksheet. How about, let's call it 203, what's a derivative? Put your name in here somewhere, so if we print it, you know the printout is yours. And today is, what is this today, the 22nd? Alright, so what it is, who it is, when it is. Okay? Bing. What it is, who it is, when it is. So give this thing a title, put your name in there, put the date in there. Today's date, yep. Alright, so number 10 says, do you have your sheet? Page 92, actually it's 93, number 10. Alright, in questions 9 through 12, at the indicated point, find the slope of the curve, an equation of the tangent line, an equation of the normal line, and then graph all this stuff. Alright, so in number 10, from the homework, this is number 10, we're given that y equals x squared minus 4x. Y equals x squared minus 4x. And we want to do all this stuff at x equals 1, it says. Okay? So how do you find the derivative? Do we know the rule? Do we need Sage for this? What's the derivative of x squared minus 4x? We figured this out last week, didn't we? No? We might have to do this the hard way then. Do you remember how this works? Right, the exponent thing, right, exactly. Let's go to the schmack board. Alright, refresh your memory. Yesterday, Friday, we did it the hard way using the definition of the derivative, right? We said that f prime is the limit as h goes to 0 of f of x plus h minus f of x all over h, right? And we figured out that that worked out, the power rule works out this way, remember? If f of x is x squared, we did this one, then f prime was what, do you remember? 2x. Then we also did, if f of x is x cubed, then what's f prime? 3x more 3x squared, right? So what's the pattern? We didn't do this one, but we talked about it. What do you think that is? F prime, the derivative of x to the fourth is 4x cubed. That's the rule, right? Okay, so they gave us, what did they give us? They gave us x squared minus 4x. Okay, so you tell me, if f of x is x squared minus 4x, what do you think f prime is going to be? You tell me. We did x squared. It was 2x, right? Remember what you do is you take the exponent down and subtract 1 from the exponent, so it's x to the 1, right? What exponent is here? 1, so bring it down, and you have negative 4 times 1 is negative 4 times x to the what? 0. And what's x to the 0 anyway? So you know? Okay, that was easy. Wasn't that easy? Now if you don't know it, you can do it the hard way. You can put that through the whole definition. Right? You can run x squared minus 4x through this whole definition right here. The definition of the derivative as the limit of the difference quotient. This thing is so infamous. I say famous. But it's so infamous that it's got a name. Difference because you subtract it. Or quotient because you divide it. The limit of the difference quotient, definition of the derivative. That's what we're doing. Alright? So you could do it the hard way if you don't remember, but this is just powerful. This is x to the 1, this is x to the 2, it's just powerful. That's all it is. Alright, so let's answer the question. Let's go to Sage and answer the question. We need the equation of the tangent line, right? How do you do that? Well, first of all, can you figure out let's see. What if I say f of x is x squared minus 4 times x, right? And let's say I want to display that. All right, is that pretty print? Nah, let's make it pretty print. All right, there's f of x. Now, you don't know how to make Sage do f prime, do you? So let's do it. Here we go. Let me call that g of x. Let's say g of x is the derivative. Let's see if I remember. I think it's f of x dot diff. Is that right? 2x minus 4. Is that what we said? So if you get a derivative that's really weird, you can actually just do it real fast on Sage. It'll do it for you. Who's stuck? I see some people stuck. So f of x is a given function. G of x is what I'm naming the derivative. Just give it a name. The dot diff method does differentiation, we call it. All right, so you got 2x minus 4. So you can make f of x anything you want, and you're going to get the derivative real fast, right? Look, what if... How about this? How about I put this all in one cell? Show this, and then I'm just going to copy this. Control X it, put it here. Show that. What'd I do? Well, I don't need to do that anymore. Dang it. Wait, hold it. Wait, let me fix this. I'm trying to put this all in one cell so I can do something quick. Hang on. There you go. Okay. So I put that all in one cell. So why? What does that mean? Well, because I can now change it to whatever I want. What if I make it sine? The derivative of the sine is the cosine. What if I make it cosine? The derivative of the cosine is negative sine. What if I make it tangent? The derivative of the tangent is tan squared plus 1. Amazing. Okay? You can put anything you want here. What about exp? What do you think exp stands for? Exp is a special name. It's e to the x. Look at that. Isn't that weird? E to the x is a weird function in that its derivative is itself. So you could make Sage differentiate anything you want. Give me something. Any function you want. Give me a function. Give me a mother function. Go ahead. Come on, name one. X squared plus 3? X squared plus 3. Would you agree with that? Because you know this rule. Why is it 2x? Because x squared is clearly a power rule, right? So what happens with the 2? It goes down 1 and decreases, right? But what x is here? Do you see an x here? Well, you can think of it as 3 times x to the 0. Is that the same thing as 3 times x to the 0? Because x to the 0 is 1, right? So what if you do the power rule on x to the 0? What happens with the 0? Let's see. Let's put it right here. What if I said times x to the 0? What happens to this exponent when you differentiate? What happened to this one? It came down in front and you subtracted 1 from it, right? So what happens to this one? The same rule. The 0 goes out. The 2 went out in front, right? And then the 2 minus 1 became this exponent, right? So what happens with the 0? Goes in front, but that means 0 times stuff is 0, so it goes away. It went away. It's gone. All right? Look, let's make it more obvious. What if it's cubed here? What if it's fourth here? These are just power rules. All right? The derivative of x cubed is 3x squared. The derivative of 3x to the fourth is 12x to the third. Why? It wrote it backwards. The derivative of this ended up here. Why is it 12? Yeah, what? Yeah, more. The 4 goes in front times the 3 that was there already. That's where you got the 12, right? And then you subtract 1 from the 4 and you get the 3. All right, let's go back to the question that they gave us. What was it now? It was x squared minus 4x, right? Let's not get crazy. So it's x squared minus 4x, and we got 2x plus 12. All right, now, how do you get the slope of the tangent? How do you get the equation of the tangent line? I want the equation of the tangent line. How do you write the equation of any line? Every line. Can we write it down? Y equals mx plus b? Yeah, but I don't know b. Y equals mx plus b works if you know m and b. I know m. Why? I know m. Why? Because the derivative is the slope of the tangent line. That's what it is. They want to figure this out at x equals 1. So all you have to do is plug in 1, and what do you get? Plug in 1 in here, and you get what? 44? 24, really? Here. Here, 1. 14. The slope is 14. Okay? Did I type in something we wrote? What did I do? Oh, there's an extra 3. All right. It's just 4x, right? That 3 was stuck there from before. Hang on. Yeah, I don't want that 3. That was from another problem. Okay, is that okay?
No, it's minus.
It's minus?
Yeah.
Oh, it's minus? Oh, God. So we're multiplying by a -4, so it becomes negative. Okay. All right, good. All right, so look. What if I plug in 1 here? What if I plug in 1 here? What do I get? -2, right? What if I plug in 1 here? 1 squared is 1. 4 times 1 is 4. 1 minus 4 is -3. So I know the function at 1. I know the derivative at 1. That's all I need to figure out the equation of the line. Because remember this way of doing it? By the way, this use smart notebook is weird. All right. Remember this other way of writing the equation of the line? Y minus y1 equals m times x minus x1. Remember this stuff? This is called the point-slope method. If you know any point of the line and the slope, plug it in. This is called the slope-intercept method. If you know the slope and the y-intercept, plug it in. I don't got that. But I got this. I plugged in x equals 1. I got a y value, and I got a derivative. Don't I? All right, let's do it. All right, so back in Sage, let's find f of 1. How about this? Show f of 1. You told me it was going to be f of 1. Come on, put a 1 in there. It was going to be -3, didn't you? If you plug in 1 here, do you get -3? Is that right? Didn't we do that? What if I show g of 1? Do I get what I wanted? If I plug in 1 here, do I get -2? If I plug in 1 here, do I get -3? All right. So why is that useful? Because remember, let's see, this is all number 10, right? All right. This is all number 10 stuff. All right, let's put it, I'm going to put it all in there. I'm going to put it all back in here. All right, so I'm going to write a comment to self. Ready? To write the equation of the tangent line, you write y minus y1 equals m times x minus x1. Right? So let's do that. Here we go. What? All right, you want to do it in a separate cell? All right, we'll do that in a separate cell. All right, that's all the work I need to do. Now let's put it all together.
Can we scroll back up?
Yep. That's all we did. We wrote down what f is. They gave us that. We figured out the derivative with the dot diff. Then we showed our f, or showed our g, and we showed our f at 1 and our g at 1. So that's the input. That's the output. Remember, this is people talking to people. This is people talking to Sage. And this is Sage talking to people. All right? So that's a comment. That's the input. Why is it doing that? That's the input. That's the output. All right? But I still didn't answer the question. Are you ready? I need all of this to answer the question. Now let's put it all together. What is y minus y1? Right? What is y minus y1? Well, let's write it down. Let's see. I'm going to write it down like this. Y minus. Now, which one of these was a y value? And which one of these was a slope? One of these was the y1 and one of these is the m. Which is which? Any ideas? Which one of these is y1 and which one of these is the slope? You tell me. -3 is the y1 and -2 is the slope. So let's write that. Here's your y1, -3. Here's your slope, -2. And what's your x1? What was the x value we plugged in? 1, right? So there you go. That's the equation of my line. Now, how do you subtract the negative? Add the opposite. So I'm going to rewrite this a little bit. I'm going to add the opposite instead of all this crazy stuff. Okay. What are you going to do with the -2? What are you going to do with the -2? No idea? What can you do with this? What can you do with the -2? This. No? I'm trying to get y alone so I can graph it, right? Distribute, right? Okay, distribute -2 times x minus 1. What do you get?
-2x plus 1.
All right, let's write that down. This is just note to self, what I need to do. So y plus 3 equals -2x, plus 2? All right, how do you get y alone? One more step. How do you get y alone? Subtract the 3, get the y alone. All right, so if you subtract 3 from 2, what do you get? Yeah, subtract 3 from 2, you get. Guys, I know it's been a long weekend, but, time to turn on those brain cells for a while. Yeah, subtract 3 from 2, you get? -1. Okay, so that's what I'm graphing. So I'm subtracting 3 from 2, I get -1. All right, so let's graph all this stuff. I want to graph this. This is the tangent line. This is the line that goes to the point 1, -3, x and f of x, and has a slope of -2, f prime at 1. 1, f of 1, f prime at 1. That's how you get the equation of the tangent line. What?
When you first evaluate, is something supposed to come up by answer or no?
Well, these are all comments.
Oh, so this is...
Right, I'm just going to graph. This is what I want to do. I want to graph, okay, here we go. Plot, let's graph f of x. Come on, graph. There it is. There's f of x, right? Let me make it a little smaller. All right, but now this is only graphing from -1 to 1. What do I want? Well, I want to see the tangent line at x equals 1. Am I going to see it? Let's find out. What else should I graph? I graphed the function. Now I want to graph the tangent line to that function at x equals 1. Do you remember how to graph more than one thing on the same axes? Right, we've done this. I want to graph the function and this. Put it in, well, actually it's square brackets, but yeah. Let's put it in square brackets, comma, 2 times x minus 1. So that lets me graph two things at the same time. Wait, oh, it's negative 2. Whoops, negative 2. All right, there you go. Does that look like a tangent line at x equals 1? It's just tapping, right? Now to make it obvious, probably make an x max that's bigger to see that it doesn't cross. But that's all we did. Look, this is note to self. This is human work. This is the graph to see if our work makes sense. Why does it make sense? Because we're graphing the function and the line tangent to that function, and it looks tangential. All right, there it is.
I don't get this.
All right, coming around. All right, so you got a tangent line? All right, I could change the x max so I can see more of the curve and see that it doesn't actually cross the curve more than once. Tangent lines just touch once, right? Let's see those tangent lines. One sec. All right, they're graphing from -5 to 5. Make it even more obvious. Do that in a sec. Right? That's not supposed to look. But it's the line. That's a tap. It's a curve. That's a tangent. Just tap over tap. That's tap. Well, yeah, it's a common subject. So that should affect your graph. Yeah, it's like the line is correct. It's like your F is wrong. Your F was defined up here. F is minus 4x. Are we good? You see what I see? You see what I see? You thinking what I'm thinking, Pinky? World domination? We're taking over the internet? All right. How about this? Look. Remember, if you don't tell it what x min, x max you want, it defaults to an x min of -1 and an x max of +1, right? Let's change that just to see more of the graph. Comma, -5, comma, +5. How about that? Ready? So you still get a parabola, right? Because remember, f of x is x squared minus 4x is a parabola. And you still get a line, because -2x minus 1 is mx plus b form, isn't it? And you still get a tangent line. It only taps the curve once. It doesn't cross. It doesn't hit like twice or 3 times, right? All I did was I changed my x min to -5 and my x max to +5. Right? See it? So did we answer the question? Let's see. A, what's the slope of the curve? Well, you tell me. What was the slope of that curve? What's the slope of the tangent line of that curve? -2. Good, that was part A. What's the equation of the tangent line? Part B, -2x plus 1, right. All right, part C, what's the equation of the normal line? What? What's a normal? What's a normal line? A normal line is like the tangent line, except it's perpendicular to the point of tangency. How do you know when two lines are perpendicular? What's the relationship between the slopes of two perpendicular lines? Negative reciprocals, right, okay. So what if we do the same thing, but now we make a negative reciprocal slope? What's the negative reciprocal of -2? 1/2, right? Okay, let's do this whole same thing over again, but use a different slope. All right, so the slope is 1/2, isn't it? Okay, so 1/2. All right, so we still change the sign here, but now we want to distribute the 1/2, right? So 1/2 times x is x/2, and 1/2 of -1 is -1/2. So I'm graphing, and then let's see, if I subtract 3 from -1/2, I get -7/2, don't I? Because 3 is 6/2. All right, so let's graph that. So I'm going to take this plot and change it to graph not only the tangent line, but this new line, comma, negative 2 times x minus 7 divided by 2. Let's see if we get the normal line at the same point of tangency. Okay, are you ready? Whoa, what happened? Here. Which one? The other one, That one. This one's just graphing the function x squared minus 4x and the tangent line at x equals 1, negative 2x minus 3, so minus 1, from x minus negative 5 to x max is positive 5. But now I'm going to graph that plus the normal line. See, this is the normal line we figured out. So let's graph it. And, well, it's hard to see what's going on here. Wait, that's not it. What happened? What happened? Oh, wait, it's not. I distributed the 1/2, so it's 1/2 for x, right? Whoops, sorry. I forgot the 1/2. Whoa, it's not minus 2. It's 1/2. There you go. Now, why doesn't it look like they're normal? What should they look like if they're normal, these two lines? Perpendicular, right? The problem is that the aspect ratio is messed up because I just arbitrarily made this x min and x max fit in this window. I had to change the aspect ratio to 1. Huh? I have to make it so that this scale of 2 matches this scale of 10, does it? 10 units in y equals 2 units in x? That's wrong. That's not right. So let's fix it. Comma, right here after the 5, comma, aspect underscore ratio equal to 1. Now what does that do? Look at it. Are the lines perpendicular?
Yeah.
They are. Okay, there you go. The thing is, it's hard to fit this on one graph because the y values are so big when you plug in like negative 5 into the parabola, into f of x of the parabola. Maybe we shouldn't make the too big a negative y, x min, and too big a positive x max. How about we just do it near x equals 1, the point of tangency? How about 0 to 2? All right, that's not too bad. You still see the parabola. You see the tangent line with a negative 2 slope. And then you see the normal line with the 1/2 slope that's perpendicular. All right, so I changed the x min and x max so the y values don't get too big on the parabola, but you still see the point of tangency. So you see the parabola, you see the tangent line, you see the normal line. Aspect ratio of 1 makes perpendicular look like perpendicular. That's what it looks like. It makes circles look like circles. Like if you were going to graph a circle on here and the aspect ratio was wrong, it ended up looking like a squashed circle when it's like an ellipse, like when it's not. You know, so you got to be careful with that. All right, that was question 10. Holy cow. All right, are you ready for question 20? This was homework, huh? Did you do this?
Yes.
Yeah, tonight's homework, same page, multiples of 5. Let's see, we'll go over that tomorrow. All right, here's number 20. Unless anyone's stuck on 10. That's basically all of 10 right there. Anyone stuck on 10? All right, question 20 says, what's the derivative of 2 over x? What's the derivative of 2 over x? And this you know. This whole homework is power rule. You don't need Sage for this, right? All right, this is number 20. It says f of x is 2 over x. How do you get f prime is the question. That's number 20. How do you get f prime? Hint, hint, hint. It's a power rule also. Can you write this as a power? 2 times x to the what? Negative 1, right. So, how do you differentiate that power? What do exponents do according to the power rule of differentiation? Goes down in front. So negative 1 times 2 is negative 2. And then what do you do with the exponent? Subtract 1 from negative 1, you get negative 2. Or if you like, that's the derivative. Is that right? Let's see. Let's ask Sage if that's right. We know how to do it. I'm just checking. I'm using Sage to check. All right, so number 20. Number 20 says f of x is 2 over x, right? So I'm going to say, all right, let f of x equal that. Let g of x equal the derivative. Remember how you get derivatives? F of x dot. How does Sage do derivatives for you? Dot diff, the differentiation. All right, let's show them. Show f and show g. And we know the answer. We said, what was it? Negative 2 over x squared, wasn't it? Right, let's see if that's what we get. Did we get negative 2 over x squared? Are we good at this? Phenomenal. Look at it. Yes, we did this by hand. We got negative 2 over x squared, didn't we? Look, that's what we got. There it is. We did that. We don't need Sage for this. Sage is useful if there's something you don't know how to differentiate, but you know how to differentiate every power rule there is. Okay? Okay. Now, just for fun, what if we graph them? Let's graph them. Let's see what they look like. Plot f of x. How do you graph more than one thing on the same axis? Got to put it in square brackets with a comma, right? And remember, if you don't say x min, x max, what are they? They default to -1 to 1. So here's your graph. And that's unfortunate because it's not defined. By the way, this is not defined where? At 0. All right, so that's not a good x min, x max, is it? I did include 0. That's bad. So let's change it. How about we go from, just for fun, 1 to 2. Now this graph is humongous. Okay, here we go. Now, listen. Shh. How do I know which is which? I don't know which is at 2 over x and which is negative 2 over x squared. How do I know? Maybe I should color code this. Huh? How about this? How about we say, instead of show, how about we say P1 equals plot of f of x from 1 to 2, but change its color to, I don't know, red. I'm trying to make this stand out so I know what it is. And then make plot 2 equal to the plot of g of x from the same x min, x max, and color, I don't know, what color do you want? Green. Put an equals here. Green? Okay, equals green. All right, now let's see. So instead of doing that, I'm going to do P1 plus P2. All right, so which is which? The red one, do you know which it is now? The red one is f of x. The green one is g of x. There you go. So why is g always negative? Look, these y values are below the x-axis. They're all negative y values, aren't they? Why did I expect all of these values to be negative? Why do you expect all these values to be negative? Because look at the slope of the tangent line here. Draw a tangent line in your head. What kind of slope do you get? Negative slope. That's going to happen whenever this function is decreasing. Isn't it getting lower and lower and lower? When a function is decreasing, the tangent line slopes are negative, so the derivative will be negative. Look, what if you change that to some other function? Make it any old function. How about sine? Whoops, I didn't change it here. Why is this positive then negative? Look, the green values, the y values, they're above the x-axis here. That means the y values are positive. And they're below the x value here. That means the y values are negative. Why does the derivative change sign? All right, let's make it more obvious. What if we, now this is sine, right? All right, how about if we just go from 0 to pi? See more of the sine curve. That's a pi. All right, the red curve is the sine. The green curve is the derivative. Why is the green curve positive, then negative? Any ideas? You know this. If you draw a tangent line here, what kind of slopes are you going to get? On the red line. Positive. What kind of slopes are down here? Negative. That's why the derivatives are positive, then negative. What does that mean? When the derivative is positive, your curve is increasing. When the derivative is negative, your curve is decreasing. Ah, look at that. How about if I change this to cosine? All right, the green curve is what I'm differentiating. The red curve is what I'm differentiating. Why is the green curve always negative? Yeah. Why is the green curve always negative? Yep. The y values of the green curve are all negative. That's the derivative. Why are they negative? Because this is always decreasing. The slopes of the tangent lines are all negative. That's what we're doing. All right, let's start. I know they gave us a different function, but if you get this working this way, or you keep the one we had this way. Is that working? All right, I don't really care which function you start off with at first. I just need you to realize when the green curve, the derivative is negative, what does that mean? And when it's positive, what does that mean? That the original curve, the red one, was increasing if the derivative is positive. And if the derivative is negative, that's because your function is decreasing. The original function is decreasing. All right, let's stop. All right, so anybody else stuck in this? All right, so guess what? 30 is the same thing. Well, actually, no, 30 is a little different.
We only did 2 problems?
Yeah, those 2 problems.
That's crazy.
Yeah, that's why we're going to do some more of this tomorrow. I guess we're done. We're done, okay. All right, YouTube, see ya. Yeah, bye, YouTube. All right, we'll do some more of this tomorrow. How to differentiate it, what does the derivative mean? All righty. So, bye-bye, YouTube.